Hello and greetings to everyone watching the video. My name is Manav Dharewa. I am from Integrated MSc Physics branch and my enrollment number is 19311013. This is my video presentation for the course PHN 314 Microprocessors and Peripheral Devices, and the topic of my presentation is determining the value of the Euler's quotient function for a number and also determining its divisors using the 8085 microprocessor. So what is the Euler's quotient function and the divisor, and what are the divisors of a natural number? The divisors of a natural number x are those natural numbers which on Euclidean division with x don't produce any remainder. And the Euler's quotient function, which is denoted by lowercase letter psi or uppercase letter psi of n, will count the number of positive integers k which satisfy the following conditions. The one being k has to be greater than equal to 1 and less than equal to n, and the GCD of k comma n has to be equal to 1, where GCD of k comma n denotes the greatest common divisor of k and n. N is a natural number here. So the integers k which are satisfying the above two conditions are also sometimes called the totatives of n. So what the Euler's quotient function essentially does is it counts the number of natural numbers which are less than equal to n but which are also co-prime to n. So for a prime number p, psi of p would be equal to p minus 1. So what is the approach in this program? Here I will discuss the approach in a short form, but with the help of the flowchart and examples, it would be much more clear. So in brief, the approach will summarize what has been done in the program. So let the natural number for which the value of the Euler's quotient function and the divisor is to be determined be x. So here x is taken for this case to be greater than 1. So the program can be divided into two segments essentially. In the first segment, what we do is we find the divisors of the natural number x. How? By dividing x individually by all the numbers from 1 to x and checking the remainder. If the remainder is 0, it means that it is a divisor, otherwise it's not. So we also count the number of divisors in this process. In the second segment, what we do is we check the divisibility of the numbers from x to 2 in decreasing order by each of the divisors of x except 1 and count the number of numbers that are not divisible by any of the divisors of x except 1, because 1 is also a divisor of x. By adding 1 to this count, as 1 is always co-prime to x, we get the value of psi x. Now, the reason for not considering 1 in the list of the divisors while checking the divisibility and also in the list of the dividends, that is from x to 2 and not from x to 1, would be made clear later on. For x is equal to 1, the first segment remains the same, and instead of the second segment, we directly set the psi of x equal to 1. Because of the nested loop structure that has been used in the code, the second segment will essentially cause errors and infinite loop will set in. So here is the flowchart of the program. So we start and we set the divisor counter in the Euler Totient counter C to 0 and retrieve x from the 2000 memory location. Here u is set to x, and as you can see there is a loop structure, a single loop structure, where what we do is perform repeated subtraction of u from x until remainder is less than x. So that is done by a subroutine, and if the remainder is 0, that it means it is a divisor. The divisor is stored in memory, the counter is incremented by 1 and we point to the next memory location and we decrement the u, that is we decrement the divisor. So next, if u comes down to 0, that is we have checked all the numbers from x to 1, then we go to the next step where we decrement the divisor counter by 1. So that means we would not be considering in the divisors list which would be used in the nested loop structure the number 1. So we would only be considering all the divisors of x except 1 by decrementing the value of the divisor counter by 1. So first we check, is x equal to 1, that is our original natural number, is that equal to 1? So if that is not, so then we set y to be equal to x, basically another variable, and then what we do is we repeatedly retrieve these divisors from memory. So this includes a nested loop structure. So first we consider a particular value for between 2 to x, and then for each of the divisors d from the memory except 1, what we do is we perform division by repeated subtraction. Again this division is performed by a subroutine, and if the remainder comes out to be 0 for even one of the divisor, that means it has a GCD greater than 1, and so that means the loop will end prematurely, the inner loop will end prematurely, and we realize that it cannot be counted for the count of the Euler's quotient coefficient, and so we simply decrease the value of y, that is we decrease the dividend by 1 so that we can consider all the values from x to 2. But if for a particular value of y the remainder does comes out to be non-zero for all the divisors. That means it is co-prime to our original number x, because here we should remember that we are considering the divisors of x. We are dividing the divisors of x by the particular number between 2 to x. So if that number from 2 to x has no remainder, has a remainder for every number, that is for every divisor for divisor of x, that means it has to be co-prime to x, that is its GCD with x has to be equal to 1. So what we realize that it has to be counted in the Euler's Totient function counter. So what we do is we increment c by 1, which is the Euler's Totient counter, and so we continue the process until y becomes 1. And so this process of considering new dividend and then performing division with all the divisors will keep on continuing until our dividend reaches 1. And so then what we do is we increment the data at the memory location which stores the number of divisors minus 1. As you can remember, after the single loop we decrease the divisor counter by 1, so we increase it again, and we increment c by 1 and store in memory. The reason for that is that 1 is always co-prime to x, but as you remember, we had not considered in our list of dividends the number 1. The reason for that will be made clear again, but in short we can say that it helps us in reducing the number of iterations, or it helps us in avoiding unnecessary computations. So we increment c by 1 and store it in the memory and then halt, and that is the program ends there. So this is the code explanation which explains each of the segments. As you can see, it includes a loop and the subroutine which is used for the division. It is for the code for the first segment. Don't worry about the extensive explanation. These have been written for further reading. I would be explaining these completely in the video presentation itself, using extensive examples where I would be doing a step-by-step execution. So this is the code explanation for determining the divisors and number of divisors of x. So the loop 1 here, as you can see, includes loop 1 is the loop for considering for determining all the divisors. That is, the dividend x will be divided by all the numbers from x to 1 to determine all the divisors, and these numbers would be counted by using the counter e. This is the subroutine for division. What you can see is this would be doing a repeated subtraction, division by repeated subtraction. We will explain this, or we will explore this in detail in a moment. Now there is a nested loop structure, as I said earlier, for determining the Euler's Totient function value at x for x greater than 1. For x equal to 1, we would come to in the next slide. So this one here, we can see this loop 2 is the one which will change the value of the dividend, and the loop 3 will be retrieving the values from the memory of the divisors that we had earlier determined in our single loop structure in the first segment. So that all the divisors are considered except for 1, because we had already decremented the divisor counter by 1, as you would remember. So in that way, we consider all the divisors, we consider division of the dividend by all the divisors, and if at any point we get a zero remainder, that is, it has a GCD greater than 1, then the loop 3 will prematurely end, and we won't get any incrementing of counter c, because JZ will jump the program sequence to NA2 and thus move the dividend to the next value, that is a value lower, decrement the dividend by 1. But had it been the case that there has been no GCD of that dividend with any of that dividend, then the loop 3 will be executed completely. There will be an incrementing of c, as you can see here, and then there will be a decrementing of dividend. That is, we will go to the next number in the sequence from x to 2 in decreasing order after that. So that way the Euler Totient counter works. Div 3 is the subroutine. Here, as you can see, it also uses repeated subtraction, the repeated subtraction of the dividend by the divisor from the memory. So, and if x is equal to 1, as I said earlier, when x is equal to 1, you can guess that the divisors of x is equal to 1 would be 1, and so the divisor counter would show 1. So when you decrement e, in that case, that would lead to 0, and here we have a JZ number equals s1. This being the last arithmetic instruction, this would be executed, and we would directly come to the last step, where we would increment the memory by 1, which is pointing to 2004. 2004 actually stores the content of the number of divisors, as you will see in the example. or I could explain in a brief. 2000 holds the number, original number. 2002 holds the value of the Euler Totient coefficient. 2004 holds the number of divisors, and the numbers from 2006 to up, as I was saying, you can only, as I was saying. So in 2006, from 2006, all the divisors of the natural number x would be stored in the memory. So now, originally 2004 would be storing the value 0, right? So since it would be storing the value 0, 2004 memory location would be storing the value 0, and so by incrementing m, we would increment it again to 1. Why would 2004 store the value 0? As you can see here, move a comma e, store accumulator 2004. Because of decrement e, it would store 0. So increment m would make the value at 2004 to be 1, that is equal to the number of divisors. C has not been executed. C will, as you will see, will not be executed or will not be tampered with until jz number equals s1. So it will remain 0. So by incrementing C, we will make it equal to 1. That is exactly equal to the value of the Euler's Totient function at 1. So in that way, we have we find the value of the Euler's Totient function and the number of divisors for 1. So the reason for this is, and that why we did not consider x is equal to 1 is, the reason that we did not actually consider x is equal to 1 is that as I was saying, the reason for not considering x is equal to 1 in the nested loop structure, as I mentioned earlier in the previous slide, it would be the one that an infinite loop will set in, as I have said here. So that's the reason that we had to consider x is equal to 1 separately. Also, I also mentioned why in the dividends list we have not considered 1, because that would be an unnecessary procedure, because we already know that 1 will never be divisible by any of the divisors of x when x is greater than 1, because all the divisors would be greater than 1, because we have excluded the divisor 1 already. And the reason for exclusion of the divisor 1 itself is because in the program what we do is we are dividing 1, we are seeing if the remainder is non-zero for each and every case. But had we had considered the 1 also in the divisors list, for every dividend the remainder would always come out to be 0, and our counting will, and the counting function would miscount. So that's the reason we have not considered the divisors list to consider to take have 1, the dividend list to not have 1, and for x to be greater than 1 the nested loop structure, and for x is equal to 1 a completely different jump structure. So these are the results we get for x is equal to 12. So for at 2000 memory location, you can see that we have the number 12. At 2002 we can see we have the psi 12 equal to 4. The totatives of 12 which we received from hand calculation are 15711, that is 4 totatives, as we can see here in the program. The number of divisors of x is equal to 6, you can see that, and from 2006 to 2011 all the divisors of 12 have been mentioned: 12, 6, 4, 3, 2, 1. Total 6 divisors as has been written here. So now to understand all of this better, we will run the program for x is equal to 1 and x is equal to 4 in GNU Sim 8085. So we would reset all these values, assemble the code, load it, 000, set, assemble, and first we will take the case of 4, that is x is greater than 1. So as you can see, now we had set the initialize this Euler's Totient counter C to 0, the divisor counter, the temporary divisor counter as one should say, to 0, and we had set the to LXIH HL pair to 2006 so that we can point to the memory location from where we will start storing our divisors. Then we move to loading the accumulator with 2000 and storing the value of the accumulator, that is the x, in D, because D would be acting as our divisor, the changing divisor here. We can see now. So here loop 1 will call dividend 1 div 1 the subroutine which is below here. Here it is. So let us execute it. So div 1 will load accumulator again with 2000, that is the number x. Repeated subtraction will occur and it will keep on subtracting D, and that would occur until we get a carry. Then we have to add D again to actually get the remainder in the accumulator, and so when we return we have the accumulator holding the value of the remainder. As you see, for the first iteration, the division was of 4 by 4. The accumulator was the dividend D is holding 4, and accumulator was also holding 4 at that point. So what happens is, because this the remainder is 0, so that means it is a divisor. So what happens, D is moved to M, the value of D, that is the divisor, is moved to M, and as you can see, 2006 now holds the value 4. We increment the counter by 1, we increment the memory location by 1, memory pointer by 1, as you can say, and then we decrement D again to get the next divisor. So we again jump back to our loop, call the divisor function again. Now as you would notice, the D has changed to 3. Loading accumulator again, the dividend is again received, that is 4. Subtracting repeated subtraction would result in a remainder of 1. And so now this NA1, now jump not Z will be executed, and you can see the divisors have not been stored since 3 is not a divisor also. So we again decrement D, we get now the divisor to be 2, and now I will execute it quickly. As you will see, remainder is again 0, and once the remainder is 0, JNZ will not jump the program sequence. The number 2, which is the divisor, will get stored in the memory, and you can see it is here in the next memory location 2007, and again the memory location has been incremented by 1. So now what we will realize is that D has been become 1. This is again a divisor, and now when I execute the loop, you can see the remainder to be 0. JNZ will not jump the program sequence. D will be stored in memory location M, which is pointed by the HL register pair, which is incremented every time this storage is occurring. So now 2008 now holds the value 1. Counter has been incremented every time we get a divisor, and now we exit the loop. So now we have seen that we would be having the E storing 3 value, the value 3. So we decrement E, we move E to A, and we store it in 2004. The value 2 is received. So now we, as I said earlier, because we don't want to consider in the divisor list the number 1, because 1 will cause the miscalculation or miscounting of the Euler Totient counter because of the structure of the code. So now we load accumulator with 2000 again, we move A to D. Now had it been that X had been equal to 1, we would have jumped directly to this point, which we would also come after executing the nested loop in this case, because X is greater than 1. So we come here A is refreshed in every iteration, LXIH 2006, because HL pair is used to point to the memory location. We want, after every iteration of the inner loop where we would be dividing the divisors with a particular dividend, what we want is we want to start the list again. We want to read the list of divisors again. So that's why we have to refresh the HL pair again to 2006, which is the starting address for all the list of divisors. And also we are using E as a counter here. So with the E decremented by 1, so it would only consider the divisors up to 2 in this case. So this is why E is also being used as a counter here. And so because E is being used as a counter, it has to be refreshed after every inner loop. So that's why we again cause a movement of A to E after loading accumulator with 2004 memory location, which is holding the value 2. So now we move M to B. Now you would be wondering, why did we load the accumulator with 2000 and move the value of A to D? We will see here that D is working as the dividend, and B, which is holding the value of M to B, that is, it would be taking up the values of the divisors from the list one by one, with except for 1. So move M to B, call div3. Div3 is again a subroutine for division. It's a small subroutine where D is moved to A. The dividend, as you will also realize and remember, that it is also changing and changing and changing. We are decrementing it by 1 so that we go through the list of X to 2, because we want to check for each of the dividends from X to 2 whether they are divisible by the divisors starting from 2006, which we have already calculated. So move D to A, division loop to sub B. So B, as you remember, the divisors that we receive from here. Then we go to the next step, just not jump, not carry, and again before the execution of the return, we have stored the remainder. So as you realize, the first dividend would be 4, and the first divisor would be 4, the 4 in the list. So the remainder, as expected, was 0. So what we realize here, now jump Z not A2, because the loop will end prematurely, as you can see. because it has exited the looping statement JNZ loop 3. So the loop 3 exits prematurely or ends prematurely, and we come to the statement NA2. You can see that INRC is also not executed because we realize that if it is divisible by even one of the divisors of our current list, which does not include 1, that means it is not coprime. It has a GCD greater than 1. So that's why we can prematurely end the loop. That has the advantage that there would be less number of iterations. That is, there would be less number of computations in case of numbers which are already known to be non-coprime. You don't have to consider all the divisors. So now we decrement D, look at the next dividend, move D to A, subtract immediately 0, 1H. This is done again so that we don't have to consider the dividend 1, which we know is already coprime to X. So there is no need for unnecessary computations to check that is it divisible for 4, 2, because we know it won't be divisible. So that saves us the unnecessary computations. So we jump not Z to loop 2, and thus we have a decreased dividend. The dividend is now 3. So now we again go and refresh all the elements, the memory pointer and the counter, as you can say. Then we move M to B, and now you can see the dividend is 3 and the divisor is 4. So as expected, the remainder would be 3. So this is not 0. So we will move to the next memory location, decrement the counter by 1, and then move again. We consider now the next divisor 2. Call div 3 again. The expected remainder, as you can see, would be 1, and so as I was saying, the expected remainder would be 1, as you would see before the execution of the ret instruction. The remainder is 1, and so again jump Z not A2 will not jump. INXH decrement T, E will now become 0 because it was already holding the value of 2 after the execution. You can see here. So JNZ loop 3 will end completely, not prematurely. C would be incremented because it is a coprime number to 4. So the Euler Totient counter rightfully increments its value by 1. So now we go to the next dividend, which is 2. As you can see, it is also non-coprime to 4, but it is not divisible by 4, but it is divisible by 2. So you will see that when I execute it for 2, it will give a remainder of 2. But when I execute it for the divisor 2, then it will give a remainder 0. And so the jump JZNA2 will be executed. It will, or maybe I should say, it will jump to NA2, decrement D. The counter C is not incremented by 1. Decrementation of D will result in the next decrementation of D will result in 0, 1. So the loop will exit. So now we come to the final stage where we do the final modifications to our counts. LXIH 2004, this 2004, which was holding our number of divisors minus 1, as you would remember after we decremented E by 1 here. So now we have to make it correct, and so we incremented by 1 to get the actual number of divisors. And as you realized, we did not check for 1 because it is coprime to X already, so we have to increment the counter by 1 for that case. So that's why INRC move C to A, store accumulator 2002, so we get the value 2, and then hold. So now you can see 2000 holding 4, 2002 holding 2, 2004 holding 3, that is 4 is X, psi 4 is 2, number of divisors is 3, the divisors 4, 2, 1. So that's for the case of 4. Now the special case is to be considered as the last part of this program, so that there is complete clarity of what is being done in the program. So we will reset, set the value, to 1. Now assemble, now assemble. So let's see. So now MBIC 00H, all this would be remaining the same. There would be a calculation of divisors, as you already know. So now you can see we have the divisors. There is 1. E would have been stored to 1, as you can see. So let us re-execute because we had missed that step. Reset all 2001 and assemble, or more likely reset all, assemble 1. And so now by doing a stepwise execution, when we will see that what does E hold for us. So now you can see E is holding the value 1, decrementing E makes it 0. So now 2004 will be holding the value 0, as you can see, and jump z now number equals 1 directly causes us to jump to this sequence, that is the last segment of the program already. Now 2004 was not adjusted at all at this case, or one should say it was decremented to 0, and thus this is what was stored in 2004. So now we increment it by 1 and we realize that we have got the correct number of divisors. Also, C was not tampered anywhere, as you would realize in here, because we were just counting the number of divisors up till now. So now when we do the code of increment C and store it to 2002, it correctly calculates the number of it calculates the value of psi1. So now the program halts. We have x psi of 1, or psi of x I should say, the number of divisors of 1 or x, and the divisors of 1 or x 2006. So that is the case. As a small, one could say, example again, we do the same for 81. It's a big number, but we would directly execute it, that's why. So let me just, so you can see 81, the Euler Totient coefficient, Euler Totient function value is 54. The number of divisors are 5, that are 81, 27, 9, 3, 1, all the powers of 3 up to 5. So that's all, or yeah, that's all. So thank you for watching the video, and yeah.